Today, we're going to learn about compound events when dealing with probability. The standard we're working on is MGSE7.SP8. Find probabilities of compound events using organized lists, tables, tree diagrams, and simulation. Terms to know. An independent event is when two events in which the occurrence of the first event does not affect the second event. The thing I want to pay attention to before we even get started is independent. As an adult, when you turn to an adult, you are independent. There is nobody that takes care of you. So independent means it's standing alone. It does not affect anything. It's by itself. Dependent. I always use the example when dealing with dependent when you do taxes. When your parents fill out their taxes in February, March, or April for the government, they put you down as a dependent because you depend on them. You are a dependent because you depend on your parents. So in probability, the first event affects the outcome of the second event because it depends on what happened in the first. Independent, nothing affects it. Dependent, the first one affects the second outcome. Okay, now compound events, a combination of two or more simple events. For example, rolling two dice, flipping four coins, or drawing two cards. An independent event, to find the probability of two independent events, multiply the probability of the first event by the probability of the second event. So, two independent events equals first event times second event. If two events A and B are independent, then the probability of both events occurring is the product of each individual probability. Now let's do an example. Adriana tosses a number cube with faces numbered 1 through 6 and spins a spinner shown below at the same time. What is the probability of tossing a number greater than 2 on the cube and spinning red on the spinner? Okay, so let's break this apart. Our first step here is to find the probability of tossing a number greater than 2. Okay, so the sample space is 6, so the denominator for that is 6. And then we have to think to ourselves, how many numbers are greater than 2 on a number cube? 3, 4, 5, and 6. So the probability is 4/6. Now I'm going to go ahead and simplify that, make it easier on us when we start to multiply. So the probability of tossing a number greater than 2 on a cube is 2/3. Now let's move to the second part of the problem. Spinning red on the spinner. The sample space is 4, so the denominator is 4. And then we count. 1, 2, 3. There are 3 red. So the probability is 3/4. Now the question is asking, what is the probability of tossing a number greater than 2 on the cube and spinning red on the spinner at the same time? To do this, you take the first probability and you multiply it to 3/4, the second probability. 2 times 3 is 6. 3 times 4 is 12. Simplify if needed. So in this case, the common factor is 6, and I get 1/2. So you have a 1 out of 2 shot of rolling a number greater than 2 on the cube and spinning red on the spinner. And there's the written out response of how to do this. Dependent. A box holds 7 marbles. 3 of the marbles are blue and 4 are orange. A marble is drawn from the box and not replaced. Then a second marble is drawn. What is the probability of drawing a blue marble followed by an orange marble? So, let's break this apart. Blue marble. Okay, it holds 7, so our denominator is 7. There are 3 blue. So our probability for blue is 3 out of 7. Followed by an orange marble. Now remember, in here it says not replaced. Since it is not replaced, this is a dependent problem. So you think to yourself, what would the new sample space be if I don't replace the marble? 6. There are 4 orange. So the probability of getting an orange is 4 out of 6 because that other marble was not placed in there. Now we multiply. 3 times 4 is 12. 7 times 6 is 42. A common factor is 6. 12 divided by 6 is 2. 42 divided by 6 is 7. My answer is 2/7. There's the example written out. If you want to see that, just pause the video and read. Here's another example. For an experiment, a penny is tossed. At the same time, a spinner with 5 congruent sections, number 1 to 5, is spun. Determine the sample space for the experiment. The sample space would be 5 times 2. There are 5 different outcomes on the spinner, and there's 2 different outcomes on the penny. You multiply that together, so that means there are 10 possible outcomes that could occur here. Now, let's do one together. I don't have this one written down, but let's go. What's the probability of landing on heads and the probability of landing on 5? Okay, first question you got to ask yourself is this independent or dependent? It is independent because the penny and the spinner have no effect on each other. So the probability of landing on heads is 1 out of 2 times the probability of landing on a 5. There are 5 sample spaces, so the denominator is 5, and there is 1 5 on the spinner. So the probability is a half times 1/5. So the probability of landing on heads and landing on a 5 is 1/10. Another example. Carlos has 3 comedies, 2 dramas, 2 concerts, and 1 horror movie in a DVD booklet. He will pick 2 DVDs from the booklet to play. What is the probability of Carlos picking a comedy DVD and a drama DVD? Okay, first step. Find the probability of picking a comedy DVD. Well, we have to find our sample space first. 3 comedies plus 2 is 5, plus 2 is 7, plus 1 is 8. So there are 8 different possibilities, and 3 of those being comedy. So the probability of pulling out a comedy DVD is 3/8. Now, this is a dependent problem because we're not going to put that DVD back in there. So now we want to find the probability of picking a drama DVD. There are 2 DVDs that are drama, but what will your new denominator be? What will the new sample space be? 7, because we have taken 1 DVD out. Now we just multiply the probabilities, and you get 6 over 8 times 7, 56. Common factor is 2. 3 over 28. Now, possible outcomes. I talked about this a second ago with the spinner. I randomly choose a letter from A, E, I, O, U, and Y. So 1, 2, 3, 4, 5, 6. I'm going to write a 6 above here. That tells me how many numbers there are. And a number between 1 and 18. So there's 18 numbers here and 6 numbers here. How many possible outcomes do I have? To do this, it's a lot easier than it looks. All we have to do is take the 2 outcomes and multiply them together. 8 times 6 is 48. Bring down the 8, carry the 4. 6 times 1 is 6 plus 4. You have 108 possible outcomes. Now, here is a tree diagram. A tree diagram is just another way to show probability. So in this tree diagram, we are showing the probability of landing on heads or tails when flipping a coin. As you can tell, the probability is written on the branch, and then the outcomes are at the very end. But as you can tell, this is real easy because the probability's already been done for you. On the next one, we can extend the tree diagram to 2 tosses of a coin. Heads is still a half. And then flipping it again, you're either going to go heads a half probability or tails half a probability. So now what we're going to do is we're going to take this tree diagram and we are going to use what's there to find what is the probability of going heads and probability of tails next. All you have to do that times that. And I'm going to leave it as a fraction. Half times a half, I get 1/4, which is equivalent to 0.25. It's that easy. You take these same reasoning skills when finding compound events and apply it to the tree diagram. Okay? Also, remember sum of probabilities. They all add up to be 1. Now, let's do another example. One drawer contains 7 blue socks and 7 purple socks. A second drawer contains 3 blue socks and 2 purple socks. A sock is chosen at random from each drawer. Use this tree diagram to answer the following. And as you can tell, the probability of getting blue the first time is 2 knots. The probability of getting purple is 7 knots. And then we use the branches for the second drawer in the second part of the tree diagram. Okay, so now the question is asking, what is the probability of getting 2 blue socks? So we start with the first blue, 2 knots. Okay, I don't have to do anything. 2 knots has already been given to us, so that makes it real easy for us. Now, we go blue and move over to the other blue. The other blue probability, and again, this is in the second drawer, is 3/5. Now, this is independent. You're going from one drawer to another. So we're going to take 2 knots times 3/5. That's going to be 6/45. And then we simplify that fraction. A common factor of 6 and 45 is 3. And I end up getting 2/15. Now, let's do another one. A drawer contains, okay, I'm not going to read all that, it's the same probability, but the question is asking, what is the probability of getting 2 socks of the same color? Okay, so that means we need to do blue first, and then we'll do purple, and then we'll add the 2 outcomes together. So let's do blue first. We already did that, so it's 2/15. So blue is 2/15. So now we got to find purple. The first one is 7 knots times 2/5, and I get 14/45. That cannot be simplified. Does not have a common factor. So I'm going to add the 2 fractions together. But first I want to convert this to where it's the same denominator, and I get 6/45, and I add that to 14/45 because I want to know of getting the same color of the 2 socks, what's the total probability? So I'm going to add the 2 outcomes together, and I'm going to get 20/45, and then simplify by 5, and I get 4 knots.